hello everyone. My name is Simon Nava. We're team number 1. My colleagues are Kevin Hernandez and Christopher Ferrer. We're going to show you the specimen handling automation system for clinical usage. Follow statement will be our system basically is a concept for the basically for automating vial handling. Okay, clinical lab this specific type of solution nowadays because they want to increase productivity, they want to increase cost. Actually decrease cost, and they want to pretty much decrease the human factor in their processing times. They want to reduce the overall operating cost, like I said. They want to minimize eliminating human error, and that's why there's this desperate need for this type of system.
Okay. Here we have how the project was divided: fluid system design, the volumetric flow calculations, and the repeatability test. I was in charge of the RAM, the TVM design, the algorithm testing, and the optimization of the machine. And everything, all other responsibilities was a collaborative effort amongst ourselves. Here we have the AutoVial System. This was our original SolidWorks model before we started designing. Here you can see the RAM, the GDM, the VTM, and the tank system and the structure. This is what we have, our final product, after we designed it and whatnot, as you can see over there. Next. Design components. We took all our design components basically from Vex Robotics. They had everything that we needed, all the structural stuff, the motors, the controller, limit switches. It made the design much simpler and easier to have it all readily available to us online.
One of the best features of the AutoVial system is its flexibility when it comes to size and design. We utilized that feature and made a simple wood design that the robotic arm module, or the RAM, will basically provide the X and Y movement for the task that is needed. It does this using a rack and pinion system in both directions.
This will be the grabber dispenser module, or GDM. This was the first version that we came up with. The problem with this was that the actual dispenser was to the side, and it will interfere with our vials. So we decided to put it inside the grabber here, so that we eliminate processing time of the machine.
Okay, and the valve tray module, the VTM. This here takes care of the X-axis, considering that the robotic arm only does the X and Y. This does the Z-axis. Sorry. Basically, all this is we have the unprocessed station here, and then we have the processed vial station here. The user will manually put in the vials in that area, and then when you turn on the machine, the vial system takes care of that. It transports it over to here, and since that
the fluidic system completely depends on fluid capacitance and gravity. We don't have a tank involved in it, and it will be applied in future modifications.
Okay, in order to control our motors, our sensors, we use the Vex Robotics microcontroller. So you can see here, these ports are for the motors, and these ones are for the analog and digital input and outputs. These also can be used for the motors, so it's really expandable. It's really scalable. This Vex Robotics microcontroller. As to the design alternatives, okay, instead of using wood this is just for the prototype, but instead of using wood, we would use structures like plastics and stuff instead, and sheet metal. Okay, we definitely don't have the money to build a real prototype, so we came up with wood for this time. As to the actual arm, the robotic arm here, instead of definitely do a lead screw type of mechanism, and that will also, we'll be able to encode the shaft better. For the fluidic pump addition, we would actually have to add this pump in order to better provide the volumetric flow rate that we need. And as to the servo motors, instead of using servo motors, in real life we would actually use the stepper motors because we have more torque with them, more torque capacity, and they're more flexible when controlling them.
Okay, here comes programming. Another reason that we chose Vex is the simplicity in the program. This is a sample of our actual code that runs the system. It's a simple drag and drop system. Here you have a tree of pre-programmed functions like your for loops, while loops, do loops, such as that. You can make your own sub-functions. You can recall them multiple times, as many times as you want. Here it gives you the breakdown in C, in actual C code, so you can quickly check if it makes sense, if you're doing it right. And the setup actually helped us a lot in optimizing it. It kept everything nice and neat, and we didn't have to read through a whole bunch of code and trying to find where we made a mistake and this and that. So, next.
VDM and the VDM, and any other error handling that we need.
In the case of mass production for this, we would actually have to have a better program. Okay, that's why error handling comes in handy here. This would be an example of our actual algorithm that we're using without error handling. And then this is the flow chart. If there's a vial, then the system will run. If not, then they won't run, because there's fluid dispensing. So you don't want the vial to just put, just output fluid. And this is an overflow prevention. See if every vial will just gauge its volume, but what if there's overflow? So there are sensors that we can use for that we can add. As to the testing, the program worked successfully. We programmed it, we tested. As to the AutoVial, it's fully integrated. You can see it there, and it's actually optimized. We were able to actually achieve a throughput of 400 vials per hour, and this is a half the speed. Okay, this actually right now will run, as you will see it later, a half the speed system. As to the fluid dispensing flow rate, we can dispense 3.09 milliliters per second at full capacitance. Remember, we're using this for this flow rate. Now we can increase this by putting a pump. And with this, we're going to show you a demonstration of it. The VTM moves forward